compute a winning region, which is simply the set of states from which we can win the game, and how we can then use the intermediate results that we came up with when computing this winning region to compute a winning strategy to always win the game. We will now do the same for other kinds of games. And the next kind of game we will look at is so-called safety games. What is a safety game? Again, the game graph is the same as usual, only the winning condition is now defined a bit differently. Again, the winning condition is defined via a certain set of states f, but this time the meaning of this set of states f is that it is a certain set of safe states which we must never leave. So a play is won by the system player if this state sequence never leaves this region of safe states f. Formally, we can write our winning condition like this. The winning condition evaluates to true, which means that we win the game, if for all states that appear in our play, we have that the state is part of our set of safe states, f. Also here, some illustration. Again, the box represents the set of all states. F now is our region of safe states, which we must never leave. And again, this red line here is our play, so the sequence of states that we have executed. Question to you again, is this first play here won by the system player, if this is a safety game? Yes, because we never leave this region of safe states, so it's won. What about the second one? No. Because actually we leave this region of safe states not only once, but infinitely often, assuming that this part here is repeating. What about the next one?
No, because it's outside.
Right. Stays in F is a bit vague, but if you look at the definition, the formal definition, it really says that every single state must be part of F. So this is also lost because this tiny little part here of the play is outside of the set of safe states. What about the last one?
Lost.
Totally lost. Good. Again, as before, we can also define the winning condition using such a function oc, which gives us the set of all states that occur in the play. The set of all states that occur in the play must always be a subset of the safe states. So no states that occurs in the play must be outside of it. Good. How can we solve safety games? Again, we will do the same thing as before. We will see how we can compute a winning region on an example. Then we will develop an algorithm to do this systematically. And third, we will think how we can turn all this into an algorithm that computes a winning strategy. So let's do the same thing that we did before. Let me just see what actually f is here. Everything except 6. Okay, so our task is now as follows. We are given this game graph. Now we say that this state here is unsafe. This is the really problematic state that we must never visit, and all the other states, all these states, they are safe. This is our region F of safe states. Now, what we would like to compute is the winning region, so the set of all states from which we can enforce that we never leave F. As a starting point, we could start with F being our first guess of the winning region. But my question to you now is, are there any states that you can spot which are maybe problematic, which should not be part of our winning region, for which we cannot enforce that we stay in the region of safe states? Q5? Yes. Why?
Because it's an adversary state.
Right. So here the evil guy gets to pick a successor and it could pick this successor. So whenever we end up in Q5, then we are in trouble because we cannot guarantee anymore that we do not leave our region of safe states. So what we must do is we must avoid that we ever get into this state 5 also. From state 5 we cannot win, so state 5 cannot be part of our winning region. So our next best guess of our winning region, let's say, is this set of states with Q5 excluded. Are there any more states that are somewhat problematic?
Q4.
Q4, yes. Here, actually it doesn't matter if it's a circle state or a box state because it has only one outgoing edges. The only thing what can happen here is that we go there, and from there we already know that we have a problem, right? If we are here, then the evil guy can just pick this edge and we are dead. So we must avoid that we ever get here, but we must also avoid that we ever get here. So this state can also not be part of our winning region. So our next best guess of the winning region is maybe this one. Can you spot any more states that are problematic?
Q2. No. No. No.
Q2 is lucky because it has one outgoing edge back here. So we can avoid worse things.
We're done.
We're done, right. So from Q2 we can avoid falling out by going here. From Q1 we can avoid falling out by going here. These two states are also good because here Q3 can only choose between 1 and 2. From 1 we can go there and back. From 2 we can also go back. So from 3 nothing bad can happen. And from 0 also nothing bad can happen. We can go here, but from here we already know that we can go back. And from here we also know that we can go back. So there are no more really problematic states, and this is our final winning region. So the set of all states from which we can enforce to win the game, from which we can enforce that we will never leave our region of safe states F. Good. Now, you also have this in the slides. Let's do the same thing as before. Let's try to come up with an algorithm which computes for us this winning region in a systematic way. And again, for this algorithm, we will use this force operator that we have already introduced before. Remember what this force operator does is it takes as an argument a set of states and it returns a set of states, namely a set of 4 states from which we, the system player, can enforce that we reach X in exactly 1 step. Now, your task will be, just as we did it before, to come up with an algorithm which computes the winning region in a safety game using this force operator. Again, as an inspiration, you can look at the steps that we did manually on the blackboard. Then this may already give you a hint how you could define the algorithm. Probably I should turn on the light back again.